Okay, hi everyone. Welcome to this week's C3 AI DTI seminar series. My name is Manxi Wu. I'm a postdoc at Berkeley ECS and a research fellow at Simons Institute. I'm co-hosting this semester seminar series with Professor Sastry and Professor Srikant of the Institute. C3 AI C3 AI Digital Transformation Institute, the C3 DTI, is dedicated to supporting the science and technology development for digital transformation. This weekly seminar series features research that focuses on studying how artificial intelligence, machine learning, and big data analytics can lead to scientific breakthroughs with large-scale societal benefits. We want to acknowledge the support from our academic and industry partners. This semester series has a special focus on incentive design and learning for societal systems. We have confirmed a line of wonderful speakers, so please be sure to subscribe to our YouTube channel and our newsletter to follow the whole series with us. To find the past talks, we put all the speaker information and talk abstracts on our website. We will try to post the talk videos and slides in a timely manner, but you will eventually always find them on these websites when they're ready. Also, please subscribe to our newsletter so that you don't miss our events. Today, it is our great honor to have Professor David Shmoys to present his work on algorithmic tools for US Congressional districting fairness via analytics. Professor David Shmoys is the Leib Professor and Director of Center for Data Science and Enterprise Society at Cornell University. He has obtained his PhD in computer science from University of California, Berkeley, and has held postdoctoral positions at MSRI in Berkeley and Harvard University before. And before joining Cornell, he was a faculty at MIT. His research has focused on the design and analysis of efficient algorithms for discrete optimization problems with applications into scheduling, inventory theory, computational biology, and computational sustainability. And recently, he also focused on data-driven decision-making in the sharing economy. Professor Shmoys has served on numerous editorial boards, and he has won many awards in various societies, includes Informs, ACM, and SciM. For this seminar, the talk will be around 50 minutes, and for the audience, please use the Q&A feature to submit your questions, and we will ask them to the speaker at the end of the talk on your behalf. Professor Shmoys, the floor is yours. I will stop sharing.
Thank you, Manxi. It's a great pleasure and honor to be asked to speak in this distinguished series. Hopefully my screen is visible and all technology seems good. You hear me and all this. I don't know if someone can give me a thumbs up somehow. That'll be good.
Yes, David.
Great.
David, we're not seeing your video.
Yeah, if you want to open your video.
How about now?
Yes, it's good. Thank you.
Great. Super. Thank you very much. And again, glad to be here. Love to be able to give this talk in person. And I have to admit that in spite of a couple of years of practice through the pandemic of giving talks this way, the old dogs don't learn new tricks so well, but hopefully this will all go well. So I'd like to talk to you today as a collection of work that has to do with a problem that's very much in the news, that of taking the results of a census, as we've just done in 2020, and computing congressional districts based on that. Whoops. And of course, the starting point for this is the US Constitution, which Section 2, Article 1 says the actual enumeration shall be made within 3 years after the first meeting of the Congress of the United States, and within every subsequent term of 10 years in such manner as they shall be by law direct. Section 4 of Article 1 says the times, places, and manner of holding elections for senators and representatives shall be prescribed by each state, by the legislature thereof, but the Congress may at any time by law make or alter such regulations. And this means that in 2021, there'll be 428 congressional districts drawn, 1,938 state Senate, and 4,826 state House districts that will be redrawn, and redrawn by a collection of different rules that apply state by state. And I mean, this is an algorithmic, this is a data science, a data-driven question. And one wants to just start, take a step back, and what are the most appropriate goals and what are the most appropriate mechanisms of doing this? And I'm going to try to compress into the next nearly 50 minutes the highlights from two papers that I was recently involved with, one with a former undergraduate student, now a PhD student at MIT, Wes Gurnee, Gerrymandering, column generation heuristic for fair minus optimized political districting, and a more recent paper with my new colleague at Cornell Tech, Nikhil Garg, with Wes and with David Rothschild at MSR on combating gerrymandering with social choice, the design of multi-member districts. So as you think about redistricting, there are really two sort of goals that you might, a number of goals that you might have in mind. And one thing that as you think about a set of a district plan for a given state, one, and there are many ways of thinking about this, but for a simplifying point of view, you might just want to think about how does the vote share for a given, let's say, two-party system, as we predominantly have in the US, for one party or the other, translate into a, well, how many seats that each party wins. And we'll think about a goal, a desiderata might be that should be proportionate, that if you get 43% of the vote, you should get something like 43% of the resulting seats. Another criterion, which is often part of the discussion, is that the district should geographically reflect cohesive communities. And this gets translated formally into notions of compactness, and there are many such ways of thinking about compactness. And the underlying reason why this is the case is that there is the historical notion that representatives who come from that district should be local and live close to the communities they represent. Compactness is often used as a proxy for how to think about unbiased and fair districting, but it's important to bear in mind that proportionalness and compactness are competing metrics. So here I show you two maps of North Carolina. On the left, there's a map that is proportional, but is not very compact. Whereas on the right-hand side, there's a map that is compact, but not very proportional. And these are not the only goals that one might want to have in mind. Another notion that one might want to bear in mind for a given districting plan for a state should be notions of competitive districts, that if you have too many districts where the elections are not likely to be close, that can be viewed as a problem. If elections are close, this pushes the two parties to not nominate extreme candidates. And so competitiveness helps moderate the discussion in overall politics. And then you want as there's sort of a natural notion of responsiveness, that as I think about the vote share for a given party VP change, you want the seat share to reflect that as well. And I want to raise two distinct challenges. One, which is, I think, much more present in people's minds, and that's the notion, the first one is notion of what I'll call intentional gerrymandering, where the intention is really partisan driven, that a map is being drawn to specifically favor one party by the party in power in charge of drawing the map. And here I'll give a stylized example of a state with 50 districts. It's 60% blue and 40% red. And let's say there are 5 congressional districts that the 50 precincts should be divided into 10 precincts per district. And imagine that the precinct is either all blue or all red completely. And there's this notion of cracking and packing, in the sense that if you look at the middle map here that I'm highlighting with my mouse, that in this map, the blue party in control has managed to crack the red vote such that the blue party actually controls all 5 districts. Whereas in the map on the right, the red party, if they were making the map, has managed to pack all of the blue vote in such a way that in spite of the fact that they're a minority party, they managed to control 3 of the 5 districts. This is not just a stylized example. This is something that is very much a present part of our state by state, day by day existence. One particular notable and very much in the news example is the state of North Carolina, which had its districting plan thrown out at some point by the Supreme Court, where the vote share is roughly 50-50. In this case, that particular vote was 40-50-48, 2% for minor parties, but nonetheless, the 50% corresponds to winning 9 of the 13 seats. In contrast to this, there's also a second challenge, which is perhaps less in the news, which I'll call natural gerrymandering, and that's that the distribution of voters makes it actually impossible to draw reasonable proportional vote maps. And the prototypical state in this case was highlighted in a paper by Duchin et al. And is often referred to as the Massachusetts problem, where the Republican vote in Massachusetts is sufficiently diffuse and consistent that it is a challenge to draw even a single compact district as part of a plan in which the Republicans would naturally control that district. So this is a second kind of gerrymandering that comes into play, and we'll also talk about addressing that. But now let me sort of give a sort of more mathematical formulation of the problem at hand and introduce some of the notation I'll be using throughout for what I'll abstractly call the political districting plan. We go, let me sort of raced ahead a little too fast. So we have a collection of basic geographic units. We can of course represent that by its dual graph with a node for each sort of, I shouldn't say district, each sort of atomic unit, which I'll call block. And that we can represent each block by a node in a graph and represent adjacency by the corresponding graph. So we have the atomic geographic blocks, which I'll refer to B. We have the adjacency graph G, which has given set of blocks and edges. There are 2 key parameters, of course, the number of districts in which I want to partition this graph, and a tolerance that we'll want in terms of how imbalanced the population should be for corresponding districts. The kinds of constraints that come into play, the one that's stipulated from the Constitution is that they should be population balanced. There should be some tolerance. Typically, that's again dictated on a state-by-state basis, exactly what that means. Thinking of this as sort of within 1% is a good rule of thumb. Districts also need to be contiguous, that if I think about the graphical problem, they should be connected components in that graph, or as I think about it as sort of a physical issue, that it should be possible to walk in, without separation between any pair of points in the district. And then there's this sort of more ill-defined notion of that the district should be compact. In some states, this is actually legislated in various ways, maybe not precisely, but at least in spirit. So there are sort of 2 competing objectives, as I've already mentioned, that we want some notion of compactness and we want some notion of fairness. And up until now, I've been talking about proportionality as a proxy for fairness, and we'll come back to that in a bit. And of course, ultimately, we want a K-partition of that graph. So here we have the state of Nebraska. There are 3 districts in Nebraska, and I'm showing you one potential district plan for Nebraska. As a computational problem, this problem is hard. It is, of course, NP hard in theory, but it is also, from a computational point of view, all NP hard problems may be theoretically equivalently hard, but of course, it's really an asymptotic phenomenon. And the question is, as we think about problems with the sort of latent structure that we actually deal with and at the scale that we need to, political districting is hard in practice as well. This is a well-studied problem, both from a sort of discrete optimization point of view and also from another layer of mathematics of trying to understand the distributional point of view over possible candidate distributions to sort of use that as a metric for detecting, trying to do something that is observably unnatural, and so that there's an MCMC literature in addition to an optimization literature. I'm going to live squarely within the optimization world. And I want you to immediately think about what I'll pose as an idealized integer programming formulation. And to get you into the right spirit, I want you to think about the following very simple stylized state. It's a state that has 24 districts, perfectly rectangular in terms of what the or precinct, the 24 precincts that we want to divide into 4 districts. And we can think about as a Gedanken experiment, constructing a complete enumeration, D1 through Dn, of all feasible districts. So here I've listed one feasible district, highlighted in yellow, of the upper quadrant. But in principle, I can encode that as a 0-1 vector as to which of the given precincts or blocks make up that district, and have one column for each proposed block, and as such, I end up with a matrix that reflects the set of possible districts, and then I can introduce a 0-1 decision variable for each column in that matrix, where making that variable 1 means I'm going to choose that as one of the districts that I use for a given plan. So then, of course, we have a packing constraint that each block must occur in exactly one column that is being selected, must have be a 1 in that, and that in total that we must select exactly k districts. Of course, what makes this an idealized integer program is that, of course, enumerating the full set of districts is going to be brutally exponentially large, and that, of course, is the problem. But nonetheless, this gives rise to a natural set partitioning integer program. And here, I'm depicting one feasible solution with 4 different colors in 4 different columns that you can see that for every block, there's exactly one highlighted column that contains that block, and we've chosen the 4 districts. So this gives one feasible solution that in this case corresponds to this plan. The set that I'm interested in, of course, as a feasible set is the set that covers every block and uses exactly k districts. And what I want you to sort of think about is that, as I'm trying to optimize over a collection of how I'm thinking about maps, is suppose I don't do a complete enumeration, but I'm doing a partial enumeration of all the columns. What I'm interested in is really how dense a feasible set of full plans do I generate relative to the number of columns that I do. And I'm going to think about this ratio of the size of the number of complete statewide district plans to the number of columns that I generate, something I'll think about the leverage of how well do I leverage the generation of a not complete enumeration of the set of possible districts so as that they can translate into a plan. Now, the mere exponentiality of the number of columns in a set partitioning integer program is not itself such a daunting thing to think about overall. This kind of formulation gets used in many practical scheduling settings. Most notably, it's what runs airline crew scheduling throughout the airline industry. And that one of the key reasons that is, of course, the main technology in solving integer programs is the fact that the so-called linear programming relaxation are solvable, and handling linear programs with exponential columns is long understood to be really a question of being able to generate columns that are useful on the fly, even if you don't necessarily handle all of the columns in core at any given time. So if, for example, in this formulation for congressional districting, I had a way of sort of in an ad hoc way generating additional columns as I need them, then I'd be able to sort of use standard technology. The bad news, I don't know how to do this. I don't know how to use a standard column generation approach in order to handle this particular formulation. So what I'm going to do instead is sort of decouple 2 stages to it. On the one hand, I'm going to generate a very good enumeration of a subset of all the feasible columns. And it should be good enough in that as I think about the overall statewide plans, that we generate a rich enough set of full statewide plans to then be able to optimize over those in an effective way. And that's going to be the trade-offs that we're going to play. So now what I'm going to tell you next is a heuristic procedure. It is purely a heuristic procedure for generating a rich set of, a good set, a high leverage set of district plans. So it works as follows. It's kind of we call it a stochastic hierarchical decomposition, and it's given by a tree decomposition of the state, that at any given point, I'm going to have some subregion of the state, initially the whole state, and some number of representatives that are assigned with that. And then I'm going to randomly select a branching factor. How many subregions am I going to partition at the next stage forward? So here in this case, I'm also going to choose a replication factor. And so in this case, I'm going to, whoops, I've lost my mouse. I'm going to construct 3 possible different plans and have a division factor, a split factor that is going to be randomly selected between 2 and 5. And here in this case, I've split it into 5 regions. Here I've split it into 2. Here I've split it into 4. But I'm constructing multiple ways to split into a randomly drawn set of distinct pieces. And of course, then I need to sub-allocate the 13 representatives that would otherwise go into North Carolina, get allocated some fraction here and some fraction there. And then of course, I'm just going to recurse. I'm going to take the next subregion, and I'm going to, in this case, again, take 3 replicas of proposed splits. And I'm going to repeat that with a different splitting factor and continue until ultimately the leaves of this decomposition tree are exactly going to be places where I only have one district, one representative to be allocated to what is then ultimately left to be a district. That this is meant to exploit a kind of compositionality structure. And so at each node, we're going to have a capacity, a number of districts, and we're going to have different trade-offs depending on exactly what range of parameters. The 2 parameters that I've highlighted so far, let's call the width, the number of partitions that I'm going to generate at each node, and the split size Z is going to give the size of each partition. Am I splitting in a binary way, in a ternary, and so forth. And I'm going to separately design an optimization problem so as to do the partitioning that happens, let's say, for example, from this node down to devising this one partition. And again, there will be a sub-optimization problem that's going to be used to do that. But the picture I want you to do is to think about this animation, is to get you to understand the compositionality that comes from this overall schema, that imagine that the split that I generated at the root is indicated by this red dashed line. As I think about anything I generate to the right-hand side of that map, that can compose to be a district map, a full statewide plan with anything that gets generated to that. And then, that the next level of the tree, if I split by these, blue dashed lines, that again, any quarter is going to compose with any other quarter. And I'm going to get a sort of exponential growth now actually in the number of feasible plans that fit together like well-fitting pieces of a jigsaw puzzle. So in doing this, we can easily generate a very sophisticated set of columns here, and sort of again the yellow indicating 1, purple indicating 0, and each vertical stripe representing 1 column represents 1 depiction of an integer program that we can generate for the map of North Carolina. And so again, each column is going to correspond to 1 particular district, and then we're going to be interested in solving the set partitioning problem that's associated with things that result. But now I want to just turn and spend a couple minutes discussing how we actually do the partition. Here now we have a sub part of the state. We have some region that we're going to partition. Actually, the first thing I'm going to do after I understand that I say I want to split it into K subparts, we're going to take the overall number of representatives associated with the input region and know how many representatives are going to be required in each of the subblocks. And what we're going to do is then think about this itself as a partitioning problem where the basic decision variables that if I think about block by block is a given block assigned to the region in which is represented by that center. And there's a dispersion factor that is meant to draw that by having this as our objective, this optimization problem is geared for producing compact maps. Of course, every every block has to be in exactly one district. These two constraints ensure that they're population balanced. And this constraint is a well-known trick introduced by an earlier paper in Malhotra, which essentially says that if I think about the graphical underpinning of the regions being drawn, if I assign a given block to a given center, one of the neighbors of that block must be even closer in the underlying spanning tree that would be built to that center as well. And this ensures that we have contiguity. So all this is now setting up the machinery for building that stochastic hierarchical partition. And up until now, I haven't talked about how I ensure anything like proportionality or how am I ensuring fairness in any way. And sort of with traditional formulations, which do it on the block by block assignment way, very much in the same spirit of the partitioning IP that I just used to build one node of that tree, the objective function has to end up being a linear function of blocks. Once I've done this decoupled formulation, the objective function now can be any piecewise linear function of the districts as they exist overall. And so this allows us, if I think about an affiliation model where I use historical data to infer, let's say, a normal distribution of the vote share of a given proposed district of, historically looking back, and I model it by some normal distribution with mean mu I and standard distribution and standard deviation sigma I squared, I can then use that stochastic model of what the vote share is for that district, and that gives, of course, the corresponding Bernoulli variable, which is the likelihood of that seat going to one party or the other. Linearity of expectation allows me just to exactly model the expected deviation between the seat share and the vote share of a given state. And so this puts me in a position to exactly map that. And if you don't like proportionality, but you want something which is a bit more 0-1-ish law in terms of how we model this and thereby gets different sensitivity to vote shares, we can do that as well and think about really an arbitrary function of the vote share minus the seat share. And the way this translates into a master optimization problem as we go back to our set partitioning problem is that I can think about the cost of choosing a particular district as being that linearity of expectation of the ideal seat share minus the seat share value that results from a given vote share. And so what we end up then is an integer program. Notice this is, of course, a signed quantity. It reflects in an obvious way, is a given proposed district more Republican or more Democratic? But of course, what I want in the objective function is the absolute value of this. We want to maximize the balance between one sign and the other, not to maximize the imbalance. And of course, then what we have is just our same set partitioning integer program. So this is just exactly the integer program that I've sort of led you to expect overall, but also notice that this formulation exactly sets us up to do things like, if we want to ensure that there are a given number of majority minority districts, this can just be embedded into this formulation directly, and any number of other side constraints that can be captured here as well. So that another key aspect of the overall structure is that actually, as you sort of think about the animation I showed earlier, it's not hard to imagine that if I think about what happens at the root, there's sort of a never meet again kind of figure. If I think about the original root partition, they really generate disjoint sets of solutions in terms of district plans. And so this allows me actually, rather than optimizing a full map, really at the root, I can split that into separate optimization problems and to just run in parallel the optimal solution to the different root solutions. We can run this multiple times, and as a result, end up with a whole basket full of solutions. This is now actually coming back to North Carolina, and I can, as I think about making multiple runs that we can do, we can see trade-offs between what I can think of as the objective function of the optimization problem that I ended up with, a proportionality gap. Let's just take the simple proportionality measure that we get overall, and a measure of compactness. One simple measure of compactness for a particular state, and again, there are many that you might consider, is just to simply take the total perimeter of all of the districts that have been proposed in that state. And so you see that there really is a wide trade-off. Here, if I want to optimize the proportionality gap and really get it down to zero, here is the map that results for North Carolina. But as we're all used to thinking about sort of the elbow of the trade-off curve, we can see that by sacrificing only a little bit in the proportionality gap, we end up with a much more compact solution that's really detectable to the eye in terms of the kinds of sense of the resulting map. One thing that's sort of important to point out in contrast is that if I were actually trying to maximize unfairness rather than fairness, what we end up then is actually something which is a linear problem, and actually we can use the tree that we developed to actually solve by dynamic programming. It's a very simple, good homework exercise to give that to your algorithms class. So what that enables us to do is that for a given set of enumeration of districts, I can not only solve the integer program, but I can tell you the most democratic outcome and the most Republican outcome over that entire enumeration. And this is a state by state, at least of all the multi-district states. The single district states are clearly less interesting to do. And the graph shows that for each state, here we have Colorado, what the extremes are, and also what the outcome was in average over the thing. The bottom line is, even keeping only compact districts, so the overall scheme ensures by that partitioning IP that I showed you that the districts that we all generate are relatively compact. None of the sort of filigreed, really back to Congressman Gerry, who was the first who gerrymandered Massachusetts in the 18th century. Even with just good-looking districts, there's a huge swing of what's possible nationwide, that you can end up overall with a range between 43% and 62% expected Democratic seat share when summed over all the states. That in terms of understanding sort of competitive districts, you can get a wide range in terms of the expected number of seat swaps. But one of the most depressing aspects of all of this is that if I think about it now, coming back to that second challenge, there are only 15 states that admit truly proportional plans in terms of the feasibility. And this is a limitation. I mean, this is really the sense to which this natural gerrymandering is in fact a challenge. And what I want to use is the last 15 or so minutes of the talk to sort of talk about an alternative and to talk about a whole different range of research that provides a potential solution to the natural gerrymandering kind of issue. And this actually stems from a piece of legislation that is wallowing on the House floor, HR 4000. It's a bill that requires that ranked choice voting be used for all members of the House of Representatives, and that states are entitled to 6 or more representatives, establish sort of meta districts such that 3 to 5 representatives are elected from each district, and that states entitled to fewer representatives elect them all on an at-large basis. So this is this notion of multi-member districts that has been proposed. And what I want to show is an analysis that these tools say of really how good an idea this actually is. And something has gone wrong with, so that's the game plan. So one thing I want to do is just sort of give you a sense of, suppose we're electing N people from each district. There are one sort of natural way to do this, that each voter gets N candidates and the top N vote getters are elected. This is actually a terrible idea. And I'll talk about why that is. And in contrast to that, there's a very complicated mechanism, which I'll try to outline quickly, known as single transferable vote, in which candidates are not elected independently, but is a way of implementing the results of ranked choice voting. So I'm going to walk you through a very simple example to show you how this works. So imagine a table such as this, where there are 6 candidates, 3 Republicans, 3 Democrats. We're trying to elect three voters, 3 representatives. And we have everyone vote, and we first look at everyone's first choice. Okay. Overall, the top voter getter in round 1 gets more than a quarter of the vote. And if you sort of think about the role of electing 3 or more people, in some sense, that more than a quarter threshold exactly says that there can't be more than 3 people or 3 other people that are more preferred to that. So in some sense, that person is a lock. You, in some sense, delegate the amount needed for that, the 2,300 votes, which is exactly 25% of the votes, to that person. And then you take and you do this proportionately over the votes, the 200 votes that are dispersed in addition, and you make them go to that person, proportionately make it, excuse me, make that go to the second choice of each of those voters. And again, because you're only doing it for 200 of the 2,500, you're doing that in a fractional proportional way. This then gives a redistributed vote. In the next one, there are no new candidates that do more than a quarter. So you now discard the least popular person, and then you redistribute that person's next choice voters. That doesn't have to be done proportionally. That's done in an explicit way. All of those 1,000 votes get distributed, and you iterate as follows. The next round, the next one has to be distributed, and then finally, at that point, another candidate goes above a quarter, and then overall. So that's the mechanism of single transferable vote from ranked choice voting. And a rather simple and sort of folklore theorem is that if you have a 2-party system and you assume that there isn't sort of intra-party kinds of issues, that single transferable vote ensures that the ultimate outcome is roughly in line with being proportional. So a computational benefit of all this is that there are ways of implementing that you don't need to actually go over individual rankings, that you can actually handle this in a computationally efficient manner. So you could say, well, ranked choice voting and single transferable vote gives you something proportional. Why don't we just do that statewide? I mean, if we're going to go to multi-members, well, I mean, if you just think about California, you wouldn't want to do ranked choice voting over 53 seats that's there. And of course, it does away with this sort of notion of local representation. So one question is, and we saw this in HR 4000, how do we combine multi-member districts with a range of distribution? And we do this in a way that balances the size, the number of members in a district. And what does that do? I mean, if I go somewhere in between, can I get near proportionality? And what does that do in terms of the ability for an adversarial and intentional gerrymander to actually control the outcome? And how is that a function of exactly what's the mechanism used in selecting the multi-member winners in this multi-member district? So we do this again, full scale across every state and try to do this. And the bottom line is sort of two things. If we show that if we use either just 2 or 3 member districts, there are good reasons to do 3, not 2, with single transferable vote, that's enough to accomplish 2 things. On the one hand, we can eliminate sort of the natural gerrymandering effect to an overwhelming, to almost complete extent, and that we also inhibit the ability of partisan gerrymanders to rescale the output. And so this really gives us no discrepancy between the natural and proportional maps. And let me just show you a little bit of the data that goes in doing that, and show you sort of a composite set. So here's how to interpret this graph. If you look at the right end, where there's sort of 1 district per seat, then this is the current state of affairs. That overall, this is what the overall vote share is of the overall Republican vote share. It's a little under 50%. If you look at sort of taking the most fair solution in each state, and again, average over that state, this is about where things come up. And this is, again, fairness by proportionality by using the tools that I talked about in the first part of the talk. And I've lost my mouse. On the other hand, as I indicated before, you have this wide gap between the most Democratic result and the most Republican gap if we're going at 1 seat per district. Scale this back to 0.5, where we're going at 2-member districts or 3-member districts, you see the extent to which the natural gerrymander, the intentional gerrymandering is limited, and the extent to which that we can still maintain fairness, maintain proportionality. And I'll talk about that on a state-by-state basis in a minute. Remember, I also said that the winner take all was really a bad idea. This is what happens overall. And you see that even having multi-members actually allows the sort of intentional gerrymandering to persist all the way down to essentially 5-member districts. And it's only when you get down below that life actually starts to improve substantially. Taking a few states, an example, let's focus maybe first on Massachusetts. Again, overall, the Republican seat vote share is in the roughly 40% range. And if you only have something, by the time you get to 4 districts out of the 9 or 3 districts out of the 9, you can see that the resulting solutions that can be obtained are exactly, this is what's depicted there, of sort of the most proportional, and here are sort of the intentional gerrymanders that you could do, that you greatly bracketed in how much more people in a partisan can affect the outcome, and yet even it's with just really a few members per district, and sort of again sort of the going down from 9 districts down to 3-member districts does exactly for that. California is a case in point the other way, and California is, while in spite of the fact that it has an independent commission, you're skewing very, the map is skewing very much in the other direction. And of course, Texas is an extreme case the other sense, and there are already court cases that are already in the works from the new proposed Texas map. But again, the bottom line is if you go down from the 36 districts down to, let's say, 12 districts, you greatly limit the extent to which partisan advocates can skew the outcomes, and yet that you can draw a map that, if you control it, is very close to proportional. That this is kind of a continuous effect over the number of districts per seat. And I talked about single transferable vote. We can show that's equivalent to an inverse proportional approval voting. There's another natural rule that's considered often, that's a Thiel squared, which is also something we wouldn't advocate. But the bottom line is that even at the two-member district, that you are able to, in fact, solve the Massachusetts problem. I mean, one thing that I want this sort of the takeaway from this to be that we're this kind of full-scale analysis is facilitated by the first half of the talk, where we built the machinery not just to show the extent to which you can make things fair, but also then, of course, the analogous thing to show what the range and the dangers of what a partisan, even working on a compact set of district plans, is able to generate bias in one direction. So our recommendation is really to implement the HR 4000 with a 3-member district, which achieves the rest thing in most states. Of course, in smaller and more partisan states, it might be natural to consider larger districts. So some parting thoughts. This multi-member district is not such a pipe dream. 10 states have multi-member districts at the state legislature level. Unfortunately, they also have winner-take-all mechanisms, which is kind of we've sort of highlighted the dangers thereof. But in general, this interplay between the mechanisms for doing the social choice and the optimizing for what the districts we think gives rise to a rich literature of potential directions that people might consider. There are interesting things to think about. What are the effects at the city level? What about the role of third party? Is there a place in which they're emerging third party winners? And in general, I just hope that one of the goals of this talk is to show that we're just on the cusp of having the range of data to really show that we have the tools and the underlying ability to provide full-scale analyses that can help lay the foundations of understanding what kinds of rules give rise to what kinds of outcomes, and to help drive the agenda in this way. And with that, I'm happy to take questions.
Thank you, David. So we received some questions and comments from the audience. 4 comments from Wendy Tamtro. Just to it's kind of long, but just to quickly maybe summarize what was posted there, first is the legal landscape in terms of it might be intuitive to have proportionality, but it has been explicitly rejected as non-constitutional. And another factor is that there are other hard constraints that the algorithm needs to consider. One of these is keeping political subdivisions together. So the larger units that you use at the root node need to be the actual counties or cities in the state.
Absolutely. So let me just start by saying I agree 100% with absolutely all of these comments. And the important thing is that we've done the cleaner analysis here. We don't believe that, I'm not an advocate for a purely algorithmic solution. My goal is to be able to use these tools to put a portfolio, a basketful of proposed plans that can be then analyzed for a range of different criteria, by policymakers. And I should have said this much more clearly up front, that the goal here is to use these tools to sharpen the discussion to show what the trade-offs are. And indeed, that while proportional, and I made this clear in the original formulation, proportionality was sort of a proxy for something simple, that by having this function h overall, that we're able to actually get different, more sensitive notions of fairness that can be captured by a different h of vote share minus seat share. I'm quite sure that one can't explain this to Supreme Court, but again, this isn't a decision-making process. This is a option creating process to do that. And indeed, in terms of issues of political subdivisions, this is why it takes work. I mean, otherwise we'd be immediately in a position to join the conversation in Ohio or in Alabama or in North Carolina where the court suits are. But the point is that the tools that we've generated are exactly flexible enough to take this into account, so that although there are the political subdivision considerations, absolutely, this can be incorporated completely within these algorithmic tools. It takes work and it takes algorithmic nuance to actually augment what we're doing at a first cut to do this, but this is completely within the range of what these tools can provide. So I mean that again, this is not to say that this is an algorithmic solution. This, I see one other comment about the majority minority district, but again, this is not a focus of trying to say, here, run this algorithm, produce this solution, and this is run this algorithm and produce this portfolio of solutions that can then be analyzed because there needs to be, I mean, given the complexity and the legal nuances, this is we're not in a state to be able to handle this algorithm purely algorithmically, but we are in a position to actually create much more nuanced maps that the legal authorities can then my ideal, and then we've seen is to have a truly independent commission for each state so as to navigate this. But we've seen already some of the issues that some of those independent commissions are not as independent as we would like. So there is the the question of how do you navigate this, whether it be legislative or through the courts. But the main point is that this is a two-way street, in that a conversation between the technical piece and the political piece. And we're just in a much better position so as to be able to understand what the full range of options are by using these tools.
Yeah, thank you, David. Are there other questions from the audience or from the panelists? If the panelist has questions, please just unmute yourself and ask.
I guess I had one quick question. I think there have been other attempts to sort of come up with algorithmic solutions, right? So it seems quite reasonable that the axioms are reasonable and probably the correct thing to do in the long run. But there is a sort of maybe a game theoretic question of, right now, if you're controlling the legislature, there is less of an incentive to do this. So have you thought about what one would do to overcome that?
I mean, in some sense, I'll maintain that. I mean, I would rather. I mean, yes. So this is a generic problem, and I mean, in some sense, the political climate isn't there, but it does strike me that if one thinks about something of the nature of the multi-member district proposal, that this is something that both parties could buy into, because it is sort of a protectionist kind of, I mean, what the analysis is showing is that it builds in safeguards that allows both in one state versus the other. And again, I mean, currently there isn't a federal appetite for doing this at the national level. I mean, one of the things that the approaches that we're doing is we've been trying to look, for example, we understand that the city government in Palm Springs is interested in thinking about the role of a multi-member district for the city council, and building from a grassroots level to show what that would mean. You know, indeed, if you look at a state where it's using multi-member districts at the state legislative district, clearly the party in control is not going to want to give up the fact that they're doing winner take all, because that's really an amplification of that party dominance. But from a global, so from a statewide, nationwide thing, we do see that problems in one state are counterbalanced by problems in the other state. And so, I mean, it's not that overall the US Congress currently isn't that unreflective of the overall vote share that's going. So, in some sense, if one thinks of sort of a greater good, that might be a stable point where we're actually able to move something forward that isn't threatening to sort of a local party in control.
Thanks.
Yeah, thank you. Thank you, David. I also have a question. So I was wondering when considering, for example, between proportional voting versus like winner takes all or other kinds of voting rules, do you also need to consider like whether or not the voters are going to manipulate and untruthfully report their ranking of the candidates in terms of to best respond to the voting rule and increase the possibility of their actually truthfully wanted candidate to win instead of just reporting their truthful voting preference?
I believe, now I should think this through, and I'd want to go back and double check that these are incentive compatible. So okay. I don't think we have an issue there.
Okay, yeah, thank you. Thank you, David. Are there any other questions from the audience and panelists? Okay, great. Great, thank you. Is there another question? Oh,
yeah.
Okay, yeah. How do experiences from other democracies interact with this research? It's a great question.
One of the interesting things is that this US problem is sort of exacerbated by what I'll call the German solution, where the German solution is this mixture of local representation and nationwide representation, which serves as mitigating that. Or, to some extent, there's sort of a cultural phenomenon here. We accept as a premise that representation is local. There isn't any natural inherent thing that says that your district is represented by one of the local constituents to do this. And so the nature of the problem really is a function of the extent to which there is this sort of locality phenomenon. And so much of the same thing, is true. Now, of course, a lot of what I've posed here is very much geared around the nature of the two-party system in the US, and it's very much framed about this. How much everything would carry through for another two-party system? Very much the same. But again, it's sort of a unique set of conditions that sort of together combine for why. This is this was very much responding to a US-centric set of issues and a US set of cultural and political traditions. And I guess, looking, the comments that Wendy made, I should have made clear upfront what my overall perspective was, that this is not meant to be we're solving the problem, but this is a mechanism for generating things that should be part of the regular conversation, and not even at this level, but really has to then be refined at a state by state kind of principle for the right, parameterization and tailored. And this is something that with our team we are in the process of trying to do on a handful of states, because it is, every state is different, and tailoring the political considerations to each of those states is a non-trivial algorithmic and data management task in order to actually even just generate the portfolio for that particular state.
Okay, thank you, David. And we're about to, we just reached 2 p.m. And thanks everyone, and thanks for the question. Let's thank our speaker again for today. Yeah, thank you.
Thank you, David.
Thank you, David. Yeah.
Thanks, David.
Thanks.
Thanks, Tandy. Great seeing you.
Great to see you.
Thank you.